Am I audible? Good evening, all. I'm Pramod Gawal, TA of this course. I'm going to take a problem solving session 5 on the course Chemical Reaction Engine 1, week 5 on the reactor designs. The course tutor is Professor Vishwavarna Mandal's Chemical Engineering Department, IIT Guwahati. A brief recap, introduction and ideal batch reactor designs, and ideal mixed flow reactor design, third ideal plug flow reactor design. These are the performance equation for batch reactor, mixed flow reactors, then plug flow reactor. Right. These are the performance equation for the in order kinetics when the constant volume process for the zero order, first order, second order, and nth order. Now this is performance equation for nth order kinetics when the volume is not constant, means volume is varying. So starting from the question one with MCQ. For a mixed flow reactor operating at a steady state, the rate of reaction is given by. As you know, the performance equation for the mixed flow means CSTR V is equal to V divided by FA naught equal to tau divided by CA naught equal to XA. Right. Here is the volume. If is equal means molar feed rate and tau. This is a concentration. The convergence are either rate. So here is the rate of reaction. So RA equal to AP XA divided by the option C is right. Question to the conversion XA and resident time data are collected for the zero order liquid phase reaction in a third tank reactor. Which of the following will be the state line? Right. Here is a mention that zero order liquid phase reaction and CSTR means CA not equal to the CA is 0. So this is the equation for performance equation for the CSTRs. So K tau divided by CA naught equal to XA. Right. K tau CA equal to XA. Right. So XA versus tau. Right. So XA versus tau graphs will give a straight line with K by CA naught is a slope. Right. Take the option A is now. Moving to the question number 3. For a given conversion and first order reaction, the volume required for a mixed reactor is that of a PFR. So here for a particular conversion for first order reaction, so volume required for the CSTR then PFR. So how to calculate? So here is a performance equation for PAM, CSTR and PFR. Right. So CSTR V equal to P naught XA by K CA naught 1 minus A. Right. The first order reaction. Suppose check for conversion is equal to 0.5. So V is equal to take these terms constant like P, it's a 1, right? Systems 1. Now check for the PFR. So V is equal to P naught. After integrating, you will get K A naught ln 1 by 1 minus X, right? So V is equal to put a value XA equal to 0.5 in this equation. So we get 0.693 P. So the volume required for the mixed reactor is higher than that of the plug flow reactor. Now question for the same conversion, the holding time required in a batch reactor is always equal to rest time required in a PFR flow reactors. So is this question is a true or false sentence? So for a batch reactor, performance equation T equal to A naught integration 0 to XA dXA plus RA. And for PFR is equal to A naught 0 to XAF dXA minus RA. So for the same conversion, the holding time in batch, this is a holding time in a batch reactor equal to this is the space time for the plug flow reactors. So, always means holding time required in batch reactor also equal to the space. So it is a true sentence. Question 5. What is the exist conversion of reactant A for a zero order reaction taking place in CSTR with the following data? Rate constant given 1 mole per minute per liter. And feed concentration given 1 mole per liters, feed flow rate 0.5 liter per minute, and reactor volume is 1 liters. So you have to calculate the exit conversion of the reactant A. Here is mentioned zero order reaction. CSTR. Right. So performance equation for CSTR V is equal V divided by F A naught equal to tau divided by C A naught equal to XA minus RA. Here is a zero order reaction, means CA not equal to the zero. So Re equal to K. Right. So Xa equal to K tau into C naught. Right. So here tau equal to volume divided by volumetric flow rate. There is a volume given 1 liter and volumetric rate 0.5 2 minutes. Right. So K given, concentration, initial concentration given, and how we calculated to put it in these equations. So K 1 put out 2 plus A not 1 theta 2. It means 200. So exit conversion is 200. But above equation is valid if any reactant present in the reactor. So after a 100% conversion, all reactant are consumed. So conversion is a 100%. So 100% is a correct option. Question 6. 10 meter cube CSTR is used to decompose a dilute solution of A. The decomposition is irreversible with a first order rate constant of 3.45 hour inverse. If 95% decomposition of A is desired, the required feed rate is. So here first order reaction and CSTR reactor is a CSTR. The performance equation the first order reaction at a constant value equal to Xa by 1 minus Xa. Right. So tau Xa given the 0.95 and K given, so 1 by K to Xa 1 minus Xa. Right. So 1 by 3 by 4 5 to 0.95 to 5.5072 hour. Right. Now to calculate the feed rate, so as you know, tau is equal to V by volumetric flow. So you have to calculate this one. Is not equal to V divided by tau. So we given 10 meter cube and tau 5 point just calculated 5.572. So it's a 1.816 meter cube per hour. So this is the feed rate. Question 7. The reaction A gives B is conducted in an isothermal batch reactor. If the conversion of A increase linearly with the holding time, then order of the reaction. So here batch reactors, reaction A gives B. Here mention that conversion of A increase linearly with the holding times means XA directly proportional to the time, right? So we check from zero order reaction and performance. This is the performance equation for the batch reactor. So, for first order, second, sorry, zero order, first order, and second order. So XA equal to K T batch reactor, so T holding time divided by C naught, right? So here conversion is directly proportional to the time, right? It's a zero order reaction. So check for the first K tau 1 by X, so not a linearly proportional. This also not a linear proportional. So option is right. Question number 8. In a batch reactor, an irreversible first order reaction A gives B takes place. The reaction rate constant K is equal to zero point 0.2 second inverse and initial concentration of say A naught equal to zero point 0.1 mole per meter cube. Find the conversion of the reaction after the 2 seconds. This is the first order reaction. Batch reactors K given and concentration given and time given. Right. So we have to use this formula K tau equal to ln 1 by 1 by xa for first order reaction for the batch reactors. So K T equal to ln 1 by 1 minus xa. T. Right. So put the value K and T here. You will get a xa. So xa equal to 33%. Question 9. A homogeneous liquid phase reaction gives A R equal to K is C square. Explain with a 50% conversion in well-mixed reactors operated isothermally. What will be the conversion if the reactor is replaced by the plug flow types of equal size, all else remaining the same? Okay. So here initially given for 50% conversion, you are using CSTRs. Then at the same conditions, so what would be the conversion if you use a here mentioned that if use a plug flow types plug flow reactors? It is a second order reaction. This is a performance equation for this is a CSTR PA bar. Okay. So here like equation one, equation two, right? So here for CSTR XA is equal to 0.05. So put this value in this equation. So you'll get K tau say not equal to 0.5 means 2. Right. Now check for the PFR. So yes, it should I say right. So K tau say not for a PFR XA 1 minus XA. Right. So here is a K tau C not equal to XA minus XA. So XA equal to 66.7%. So 66.7% conversion required using the PFR. Question 10. Liquid A decomposes in a batch reactor by second order kinetics. If 50% of A is converted in a 5-minute runs, how long it would take to reach 75% conversion? So it's given T is equal to 5 minutes. So we have to calculate the time where to reach the 75% convergence. So performance equation for a second order kinetics for batch reactor K tau Ca naught equal to Xa 1 minus Xa. Right. So T equal to 5 and Xa equal to 0.5 put is equations. So Kca naught equal to 5 into. Now X is equal to 0.75. So the times how much time required to is the 75%. So to the 5 minutes. Put this value in this equation and here you A into C is equal to 5 into. So 5 minutes required to reach the 75% convergence. Question 11, 50% conversion is obtained in a CSTR for homogeneous isothermal liquid phase irreversible second order reaction. What is the conversion if the reactor volume is 5 times the original? All else remains unchanged. So here is a 50% conversion obtains CSTR and second order kinetics. So what is the conversion if the reactor volume is a 5 times original one? So V2 is equal to 5 times V1, right? So performance equation for second order kinetics for the CSTRs K tau C naught equal to XA 1 minus XA square, right? So tau equal to XA C naught K1 to 1 minus xk. Okay. So we can write down tau is equal to V by V naught, right? So xk V naught to cs minus xk. Now case 1, so k V1 equal to x1 V naught minus xk x1 here. And case 2, k V2 equal to 2 equal to 1 minus x2 here. Right. This equation 1, equation 2. Divide equation 2 by 1. So V2 by V1 x2 by x1 into 1 minus x1 here divided by 1 minus x2 here, right? So here is the x1 given. Here given x1 equal to 0.5, right? And V2 V2 equal to 5 V1, right? So put the 5 x2 0.5 means 0.5 1 minus x2 here. So after simplify, you will get x2 square minus 2.1 x2 plus 1 equal to 0. Right. So x square is 2.1 x2 plus 1. Right. So x2 equal to 2.1 plus minus 0.1 square 2, sorry, 4 equal to twice. So x equal to minus b plus minus b square minus 4 ac divided by twice. No? 0.1 plus minus 0.6440 to x2 equal to 0.0722%. Move to the question number 12. The gas phase reaction twice A gives B. carried out in isotherm PFR plug flow reactors. The feed consists of 80 mole percent of A and 20 mole percent of inerts. If the conversion of A at a reactor exit is 50%, then Ca by C naught at the outlet of the reactor is. Option given. The PFR. So here feed consists of 80%, 80 mole percent of A and 20 mole percent of inerts. Right. And this is a gas phase reaction. So for a gas phase reaction, epsilon equal to Vxa equal to 1 minus Vxa equal to 0, right? Vxa equal to 0. Right. There choice gives C. So this is 100 mole feed. So here this is then feed equal to 0 in product. So species A, B and inert. So here 80%, 0 and 20 is a total. Right. Product is 0, the 40. So due to the cytometric reaction, and inert will be the same. 16. Put this value in these equations. You'll get minus 4. Now to calculate this ratio Ca by C naught equal to 1 by Xa 1 plus epsilon A to Xa. There Xa given 0.5, epsilon calculate minus 0.4. So this relation becomes Ca is equal to Na by V. You can write down naught 1 minus Xa and V naught epsilon to Xa. Right. This is a A equal to C naught. And A divided by 1 plus 1 A. So put the value in these equations. So you will get 5 by 8. So Ca not equal to 5 by 8. So option B is correct. So moving to the question number 13. For a first order reaction taking place in an isothermal batch reactor, 80% of liquid reactant is converted to product 15 minutes. Calculate the space velocity required to achieve a same conversion in plug flow reactor and back mix flow reactors. So there is two terms, the space times and space velocity. So space time means the time required to process one reactor volume of feed measures at a specified conditions. And space velocity, a number of reactor volumes of feed at specified condition which can be treated in a unit time. So first order, batch reactor, first order reaction and batch reactor. So perform the equation K tau into ln 1 by 1 minus xa. So t given 15 minute and xa 0.8. So the batch reactor, so K is equal to 1 by T ln 1 by A, right? So for batch reactor, it ln 0.107 minute inverse, right? Now, so you have to calculate the space velocity for PFR and X-phase flow reactors. So first check the PFR. So for PFR, this time equal to full time, right? So for batch reactor, the holding time is 15 minutes. So it's the space time for the PFR is the same, means 15 minutes, and the space velocity 1 by tau, right? Divided by the years. So 1 by 15 equal 0.067 inverse. For CSTR, is a equation, the performance equation for CSTR. So K tau equal to XA 1 minus XA, right? So tau is equal to 1 by K XA 1 by A. So K we calculated here 0.107 into zero point 0.8 divided by 0.2 equal to 37.38 minutes. And space velocity for CSTR 0.027 0.027 minute. Moving to the question number 14. For a liquid phase zero order irreversible reactions A gives B, the conversion of A in a CSTR is found to be zero point 0.3 at a space velocity 0.1 minute inverse. What will the conversion for the PFR with a space velocity 0.2 minute inverse? Assume that all the other operating conditions are the same for the CST and PFR. So here you have to calculate the conversion for the PFR with the space velocity 0.2, right? And zero order reaction. So first we solve using the CSTRs, the performance equation K tau here, K tau divided by C naught equal to XA, right? XA given 0.3 and this velocity given 0.1. So tau is equal to 1 by S, so 10 minutes, right? Now K by C naught equal to XA. Okay. So XA 0.3 and tau 10 minutes equal to 0.03, right? Now for check for PFR to calculate the convergence. The performance equation for PFR for zero order kinetics A naught equal to XA, right? So here X space velocity 0.2 minute inverse given. So tau is equal to 5 minutes. So XA is equal to here K by C naught equal to 0.03. Put this equation and tau is equal to 5 minutes. So 0.03 into 5, 0.15. So 15% convergence for a PFR. The option is correct. Question 15. A liquid is decomposed in a batch reactor by zero order kinetics. The initial concentration of A is 0.5 kilomole per meter cube for a reaction time is 1200 seconds. The conversion is 40%. Assume the isothermal conditions. Right. The batch reactor, zero order kinetics. The performance equation for the batch reactor Ca naught equal to 0 to Xa. Here T given, initial concentration given, and conversion given. T is by R. It's it becomes K. So T is equal to, after integrating Ca naught, you will get Ca naught Xa into K. Right. So here T given, Ca naught given, Xa given. So you get K 1.66 into 10 to the power minus 4 kilomole per meter cube per second. So we calculate the K, first part. Now say second part, what will the conversion for the reaction time of 3600 seconds? So XA is equal to T3 by C naught. So here K calculated T equal to 3600 seconds and C naught given. So XA is equal to 1.2. So that is 120%. Right. So XA cannot be the greater than the 1. It's 0 less than XA than 1. So XA is equal to 1 means 100%. So all the reactant will be consumed before the 3600 seconds, means 1 hours. So question number 16. Uh, Homogeneous gas phase decomposition reaction 4A gives B plus 7S takes place in the isothermal plug flow reactor. The reaction rate minus RA is equal to K1 CA. with K1 is equal to 0.17 second inverse, feed concentration given, feed flow rate given. Determine the size of the reactor in order to achieve the 50% conversion. So here is a gas phase reactions. The performance equation for the gas phase reaction means changing volume. So for plug flow reactor, the performance equations for first order kinetics. So K tau here is a given 1 plus epsilon A into ln 1 by 1 minus xa minus epsilon A into xa. Right. So to calculate the epsilon, B is equal to 1 plus B xa is 0. So here the reaction given for A gives B here. So V is equal to 4 initially, and V xa equal to 1 after get 8, 1 plus 7. So epsilon the 1. Right. Now so tau equal to 1 by k, right? 1 plus uh, ln plus and is x. So put the value in these equations. So 150.172 into 0.693 and 0.5 to 5.211 second tau. So now so tau is equal to V by V naught, right? You can write down V to C naught by feed flow rate in smaller feed rate, right? So V is equal to P naught into tau divided by C naught. Put the value in these equations. So we get 8.8587 meter cube. So 8.885 meter cube of size reactor required to achieve the 50% conversion. Question number 17. The rate of homogeneous liquid phase reaction is given by minus Ra equal to Kca square. This reaction takes place with a 50% conversion in Baxim's reactor, means CSTRs. What will the conversion if the reactor is replaced bigger one, which is 6 times larger? All conditions remain unchanged. This is the second order kinetics and CSTR. The performance equation for the CSTR or second order kinetics Xa by 1 minus x square, right? So how it go? V by V naught. Here mentioned that which is the 6 times larger, means V2 equal to 6 times V1. So if say by K C A naught minus X square. Right. So V is equal to X A V naught A C S 1 minus X A. Right. So there is a given conversion 50%. So this is a V1 twice V naught A C A naught. So V naught A C equal to 0.5 V1. Right. Now for a second part, V2 is equal to given 6 V1. So V2 equal to V naught A naught to X A 1 minus X square. So here is we can write down X2. So put here V2 is equal to 6 V1 and the 0.5 V1 in this terms. Therefore 12 X A 1 minus X. So after simplifying, you will get X square minus 25 X A plus 12 0. So solve these equations. So you will get X A is equal to 1.33 and 0.75, and conversion is not greater than the 1. So X A is equal to 75%. So moving to the last questions of this session. For isothermal variable volume batch reactor, the following relation is applicable for the first order irreversible reactions. So where X is a conversion, X is a fractional change in value. For the complete conversion, K is a rate constant and T is a time. The first order kinetics mentioned there. As you know, CA by C naught equal to 1 minus XA 1 plus epsilon A XA. Right. Now first order kinetics minus RA equal to C naught 1 plus epsilon A XA dxa by dt. Right. And for first order radical or first order RA is equal to KCA equal to C naught dxa by dt. So C is equal to C naught to 1 minus XA 1 plus epsilon A to XA. Right. So write down CA equal to these sums here in these equations. So K equal to C naught 1 by x 1 plus x a equal to c naught dxa by dt. These get cancelled, right? Let integrate 0 to xa dxa by 1 minus xa 0 to t dt. Right? You will get minus ln 1 by xa equal to 80. Check the option. Here is the C is the right answer. So I covered all the question based on the reactor designs. So thank you all. So you will meet on the next Friday on next chapters.